As we wrap up the discussion on dimension reduction, let's look at application of ISOMAP and local linear embedding, and let's apply it to some images of, what is this, clothes? So this is kind of like the MNIST data set that had handwritten numbers. This one is just kind of blurry images of product. And so we actually have 10 categories here. We have t-shirts, trousers, pullovers, dress, coat, sandal, shirt, sneaker, bag, ankle boot. And so we're going to use the nonlinear dimension reduction methods to see how well we can combine that with k-nearest neighbors in order to classify these images. Okay, so let's give that a try. So it's going to be like the MNIST data set if you did that one before. And so we do have here a 28 by 28 pixel image, which gives us that 780 whatever pixels here. So we need to reduce it down. And then we're going to build our classification model. So let's just go out of here. And we are at the very end of this dimension reduction workbook here. Oh my goodness, words have left me. So we are working from the workbook that is dimension reduction. You can find it at drstephpowers.github.io/BIA. And so for this particular example, you're going to need the fashion data set. And that fashion data set comes from Kaggle, so you can either download it directly from them, or you can find it here on the left, fashion MNIST test.csv. We're just going to use a part of that data set. They have a whole test file and a train file and all these pieces. We're going to simplify it and just use a subset of it. So we're using fashion MNIST test, which means you will need to open this document in Collab, save a copy logged into your Google Drive, and then you will need to take this file and save it into your Google Drive. And then you will need to mount your Google Drive. So you will need to do from google.collab, import drive, drive mount. This will then connect your Python workbook with your Google Drive. Nobody else has access to any of that. So it'll just connect you to your stuff. And that will allow you then to do fash equals pd.read_csv. This will allow you to import in that fashion data set. The first part here up to the My Drive is going to be the same for everybody. And then it's simply which folders you put your data set into. Mine is in a folder called BIBA Handbook. And inside that's a folder called Chapter 9 for my handbook. And then the data file itself is fashion-mnist_test.csv. So we're reading a CSV and we have a CSV extension. So make sure you have all that loaded in so that we can work through this. So once you have loaded in that data set, we can take a look at it. Fash is not defined. Well, that's probably because I didn't load it in. So let's go take a look. All right, so import pandas as PD, import numpy as NP. I am connected to my drive, hopefully. If not, I will remount it. And we're doing this fash one here. So let's load that sucker in. It's always good when I tell you what to do and then don't do it myself. Okay. Scroll, scroll, scroll. Some pictures, some fashion. We must be in the right place. All right, let's load this. Okay, so we just loaded the first couple rows, but what you see is lots of pixels, and that's because we have 784 pixels to go with that pictures there, and we have labels. So just to recall, as I was showing you on that slide, is that t-shirt is 0, trouser is 1, pullover is 2, dress is 3, and so on. So let's build our model and do some dimension reduction. Okay. So what we're going to do is we're going to separate out the label here from the rest of the data from all these pixels. So we're going to take this and do fash image, which is going to be a subset of this. So let's just take code here, fash image.hid. So what you can see here is what we've done is we have taken out that very first column there, and you can see then we just have the pixels. So what we're trying to do is separate the label from the data that we're going to use to try to identify the label. So that's what this command here is that we are applying it to the columns of FASH. We're just removing that first column there. And then what we're going to do is we're going to take that column that was called label in the original data set, because we've created this new one called FASH image, and we're going to create something called FASH label, which is going to be just the label. So if we do that, and then we look at that, you can see we got one column and it's just the labels that we had in the original column here. So we've separated out our data set into two. Now we can take a look at these just like we did with the handwritten notes. So we could say, show me an example. We're going to take FASH image, index location, and I'm just randomly pulling one. So index location 2, so 0, 1, 2, it's going to be the third row here. And if we pull this information, we could get the pixels. We see the pixel 1 and 2 have nothing in them. 780, 781 have numbers. Remember that it's 0 if it's blank, and then as it gets darker and darker, I think it goes up to, what, 254 to be the amount of darkness in it. We can actually look at that particular image, so we'll do examp_image, and we'll use reshape and ravel. So we need to make sure we are running numpy as NP, and we'll reshape it into that 28 by 28. See if I got numpy running. There we go. All right, and that then allows us to plot it. So this is the matplotlib.plt, and so we can then we'll have our color map be binary because it's just shades of black and white, and we'll turn the axes off so we can see that. So make sure you do have, in order to make that all run, you'll notice I have loaded no packages here, so just so that you're knowing what I'm running here. Let's go back. That was poor etiquette. I should have written out the packages at the very top like I keep trying to train you to do so that we always have that information. So I'm just scrolling here back to the top when we had these handwritten ones. So we need that matplotlib as PLT, the numpy as NP for this. Okay, so let's go back down. Make sure I wasn't missing anything else. Scroll, 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 scroll. Okay, so we had taken our example, we had reshaped it to be 28 by 28, and we had plotted it, and so we can see here that for index location 2, we can see a picture of the image. And to get the label that goes with it, we do fashion_label, index location 2, so it's the same location, right? Same row as that. And so we get that this is item number 2, which is here a pullover. Okay. Let's do another one. We could just randomly take, let's say, index location 15. Let's call it example 2. We're pulling from the fash_image, so we're just getting the pixels. We are rearranging them, so it is 28 by 28 using reshape and ravel as our commands to get us there. And then we are plotting that information with the IMShow, and you can see we get a shoe. We can find that fashion label with our index location 15. We get it that it's category 5, which is a sandal. So in this particular case, we have sandals, we have sneakers, we have ankle boots. So we have multiple kinds of shoes. So it's not about simply identifying, just that it is a footwear. We also have, you'll notice that we have pullover, coat, shirt, t-shirt. These are very similar. So our model, the question is, can it distinguish between them? And so by using these nonlinear methods, so we're going to be looking at ISOMAP, LLE, and tSNE, we can look at, can it actually take into consideration not just the difference between data points, but also the topography of the image that has that outer shape that it needs to look at, but then also the data points related to each other. So does that extra information then help it do identification? All right, so what we're going to do is we're going to take our 10,000 data points, and we are going to separate out the testing and the training data because we do have labels, so we can do a classification model, which means we have testing and training data because it is supervised learning. All right, so why train, why test? We're going to take the first 8,000, and that will be our training data. We'll take the last 2,000, and that will be our testing data. And we're going to separate the labels, and we're going to separate the images. So the X train X test is going to be the image, and the Y train Y test is going to be the labels. All right, let's use our K nearest neighbors here. We're going to do 10 neighbors, and that is because we already know, right, that we have, where did it go? That we have our 10 categories, okay? Building a model to identify these 10 different types of pictures. So from sklearn.neighbors, we import kneighbors classifier. From sklearn.metrics, we import an accuracy score. Anytime we do a classification model, we can assess how well it is. Because this is a multi-label, not a binary, we can only use the accuracy score. We can't use precision, recall, or any of those other ones. All right, so we've imported our packages. Let's call the classification model. Let's fit the classification model. Let's predict. Call, fit, predict. So it's going to tell me that it thinks that first image is going to be a 7, then the 7. All right, let's look at our accuracy here. So the accuracy of our model is 83%. It has a harder time distinguishing between t-shirt and pullover, right, than between a 2 and a 3 in those previous models we were looking at. So we're starting here at an accuracy of 83%. Let's use ISOMAP to speed this data set up. Can we do dimension reduction here? So we're going to do ISOMAP number of components equals 10. Previously with our Swiss roll, we were doing 2, but that's only because we wanted to graph it on a 2-dimensional space. Here we do 10 components because we have 10 classes we want to label. So we'll do ISOMAP number of components equals 10. We're going to fit transform on our fashion image. So let's do our dimension reduction. And then once we've done the dimension reduction, then we'll just repeat the process of using our K nearest neighbors with 10 neighbors. We'll take our dimension reduced data and separate it out to train and test. We'll call the model, fit the model, and then we will predict with the model. So anytime we're doing dimension reduction, it can take time. So I'm just going to pause the video and then we'll resume once it's done. So we can see here that ISOMAP took about 3 minutes to process. And so in this case, right, we ran it before without it, it was quite fast. So probably not as necessary here. But let's imagine that these pictures are in color, have way more detail. Maybe we have more than 10,000 of them. And so we would do this dimension reduction. All right, so then we're going to separate out into our labels and our image pieces. So we're separating out the testing and training data. We are running our nearest neighbors. We are fitting it. We are predicting our values. And then we're checking our accuracy here. So we could see in the previous version, the full version, 83%. And in this case, with our dimension reduction, we're sitting here at 80%. Okay. So we're only losing a little bit of accuracy as we're reducing down. And so if you want to see then, you know, it's predicting how well this works. Let's just pull one. So let's take fashion image index location, I don't know, 9001. We'll call it example 3. Okay. And then let's use our reshape and our ravel to just create the image. So we're turning it into 28 by 28. And then we're going to use plot IM show to create it. All right, a bit of a black blob here. So let's look at what it predicted and what it actually is. Now we chose index 9001, which then if we remember we separated so that 8,000 went to the training data, and then the rest went to the testing data. So the corresponding number here from our data is that the predicted value here, why isn't the, let's go back, why, because we separated out. We'll just do fashion late. No, we want the predicted value. So in terms of the predicted value, right? So this is from our predicted. So the number here is going to start at 0, and it's going to go through, and it's going to go through to 2,000. And what we want is in the grand scheme of things, we wanted number 9001. So that's actually going to be predicted space 1,000, because 0 is going to be first, so 0, so it's going to be shifted 1. And then the actual label here is 2. So it is predicting that it's a 4. It's predicting that it's a coat, and it's really a pullover. So if you are going to check the images, just recognize that when you separated them out, it restarted the count at 0. And so there is a difference here in this numbering system that we have to account for. Okay. So if we want to use a different approach, let's say we want to try the local linear embedding. To do local linear embedding, we would say our number of components is 10 because we have 10 classes. And then let's run this local linear embedding to do our dimension reduction. And then the process is the same. Separate them. And then we're going to call our k nearest neighbors, fit it, predict it, and then see how well it worked. So let's run that. So our local linear embedding took 2 minutes to run. So now that we have done our dimension reduction, we can then separate our training and our testing data. We can run our k nearest neighbors with the 10 as the k to match the number of labels that we have. We fit it, we predict it, and if we run this particular one here, we get a 77% accuracy compared to the ISOMAP one that had an 80% accuracy. So you can see with these dimension reductions, there's not an expectation that it's going to be the same level of accuracy as the actual data itself. But we use these methods when the data set is so big and it's so time consuming to run any type of analysis that we need to simplify it down. So we take the time to do the dimension reduction so that we can spend less time doing the classification or cluster models. So local linear embedding, we talked about the difference between the two. So if I just go back into our slides here, right? So the ISOMAP used a geodesic approach, looking for the shortest distance between 2 points, similar to the PCA in terms of that shortest distance, but it allowed for nonlinear. So it allowed for polynomial type movement, whereas the local linear embedding just went short little stints here, moving from one data point to the next. So it's using more of a nearest neighbors approach, which means it doesn't have to be a smooth line or a polynomial type curve, right? It's not restricted to curves when it does that local linear embedding. So that's an option as well for this model, and that gave us a 77% accuracy. And so if we look at, because we've been using the same one, so we look at what is it able to predict for here. Did it get this one correct? In the previous ISOMAP, it was incorrect. It called it a coat when it says it should be a pullover. Well, let's see how well this one did. with this particular random example. Looks like it also labeled it a coat. Let's try, before we leave here, let's try the tSNE. The challenge we'll have here is that the number of components is limited to 2. So you can't make it be 10 and match the number of classes that you have. So of course the risk here is that it is reduced too much, that we'll lose a lot of accuracy because it can't represent all the variability. But we will, I don't know, let's just give it a try. So we'll make the perplexity low so that it is a small number of nearest neighbors, so perhaps it can find these different numbers here. So let's first run this. So the tSNE here took about a minute to run. So once we've done that dimension reduction, again, the same process as always, separate out the test and train. And I don't think I'm separating out the right information. Let's change that. It shouldn't be ISO because this should be tSNE. tSNE and tSNE. All right, so let's make sure we're separating out the right information. Let's try that. Okay, now let's run our k nearest neighbors with 10 neighbors. Note again that we had 2 components here with that tSNE, and we have 10 classifications. So let's fit this. Let's predict. Okay, and then let's check the accuracy here. I was able to get it here at 81%, so not bad. About better than the LLE approach here. And then we can check, might as well check that same one. So check that same one here, and what do we get for this one? Still 4. So trying to find the difference between, can't quite find it. We could change the perplexity to a higher number. If we want, we could run it again and still check that accuracy. So that's an option for you as well. So you can see in this case, we're attempting to identify these images here of this clothing, of these shoes. This one has a challenge, right? Because how close the t-shirt, the pullover, the coat is just the same thing but longer. So it does have trouble identifying some of these images. It has a much harder time than the handwritten digits. And so we can look at creating models to be able to identify pictures when they're much more nuanced. And in fact, when we get to our neural networks, we can start building more complicated algorithms for doing image recognition beyond kind of the simple ones that we're doing here that have multiple hidden layers of information to help catch more of those nuances between the different categories.